Let's talk about hydrogen bonds. Depicted here, I have three different types of molecules. On the left, I have ammonia. Each ammonia molecule has one nitrogen bonded to three hydrogens. In the middle, I have something you're probably very familiar with. In fact, you're made up of it, which is water. Each oxygen is bonded to two hydrogens. And then here on the right, I have hydrogen fluoride. Each fluorine is bonded to one hydrogen. Now, why are these types of molecules interesting, and what does that have to do with hydrogen bonds? And the simple answer is, in each of these cases, you have hydrogen bonded to a much more electronegative atom. Even though these are covalent bonds, they're going to be polar covalent bonds. You are going to have a bond dipole moment that goes from the hydrogen to the more electronegative atom, from the hydrogen to the more electronegative atom, from the hydrogen to the more electronegative atom. The more electronegative atom is going to hog the electrons. The electrons are going to spend more time around that. So that end of the molecule is going to have a partial negative charge, and then the ends with the hydrogen, those are going to have partial positive charges. Another way to think about it is if you added these dipole moments, you would have a net dipole for the entire molecule that would look something like that. So we are dealing with polar molecules, and the polarity comes from both the asymmetry and you have a very electronegative atom bonded to hydrogen. Oxygen, very electronegative atom bonded to hydrogen. So this end of the molecule is partially negative. This end of the molecule, or these ends of the molecule, are partially positive. For hydrogen fluoride, this end is partially positive. This end is partially negative. And so what do you think could happen when these molecules interact with each other? Well, the negative end of one molecule might be attracted to the positive end of another. Or another way of thinking about it is the nitrogen end right over here of this ammonia could be attracted to one of these hydrogens that has a partially positive charge right over there. Or this hydrogen, the partial positive charge, might be attracted to that nitrogen that has a partial negative charge. And this attraction between the partial positive hydrogen end and the partially negative end of another molecule, those are hydrogen bonds. And they are an intermolecular force that will be additive to the total intermolecular force from, say, things like London dispersion forces, which makes you have a higher boiling point than you would have if you just thought about London dispersion forces. And to make that clear, you can look at this chart. You can see all of these molecules are formed between group 2 elements and hydrogen. In fact, all of these molecules have similar molar masses: methane, ammonia, hydrogen fluoride, and water. If we were just thinking about London dispersion forces are proportional to the polarizability of a molecule, which is proportional to the electron cloud size, which is proportional to the molar mass. Now, if all of these have similar molar masses, then you would say the London dispersion forces must be similar, and if that was the only intermolecular force at play, they would have similar boiling points. But clearly, you have much higher boiling points for the water, the hydrogen fluoride, and the ammonia, which implies there's something else other than the London dispersion forces, and that is the hydrogen bonds. Now, many of you might be thinking, hey, hydrogen bonds sound a lot like dipole-dipole forces, where you have a permanent dipole in one molecule and a permanent dipole in another molecule, and the positive end of one is attracted to the negative end of another. And if you're thinking that, you would be correct. Hydrogen bonds are a special case of dipole-dipole forces. Why do they get their own name? Likely because we just see it a lot. We see this phenomena where hydrogen is bonded, covalently bonded, polar covalently bonded to a much more electronegative atom, and we're usually talking, especially in a first-year chemistry class, about nitrogen, oxygen, and fluorine. And so that will create this dipole, which will then make that molecule attracted to other molecules that have a dipole. And so you can imagine, it doesn't even just have to be hydrogen bonds between a like molecule. You can have hydrogen bonds between an ammonia molecule and a water molecule, or between a water molecule and a hydrogen fluoride molecule, because they all have this permanent molecular dipole. And I mentioned that these are really important in biology. This right over here is a close-up of DNA. You can see that the base pairs in DNA, you can imagine the rungs of the ladder, those are formed by hydrogen bonds between base pairs. So those hydrogen bonds are strong enough to keep that double helix together, but then they're not so strong that they can't be pulled apart when it's time to replicate or transcribe the DNA. And you'll learn more about that in biology class. Hydrogen bonds are also a big deal in proteins. You learn in biology class that proteins are made up of chains of amino acids, and the function is heavily influenced by the shape of that protein. And that shape is influenced by hydrogen bonds that might form between the amino acids that make up the protein. So hydrogen bonds are everywhere. There are many hydrogen bonds in your body right now, mainly, not just because of the DNA, mainly because you're mostly water. So life as we know it would not exist without hydrogen bonds.